Can you guys hear me? All right. All right. I'm Elena Manjavacas. I'm an astronomer at the Space Telescope Science Institute. And today I'm going to talk about some very cool, nice John Brondorf spectra observed by the spec. And what we have found so far from these super nice high resolution, high signal to noise spectra. And of course, these results have been already published, so you can go check in this QR code the paper with all the details about all the analysis that I did, because today I'm just going to focus about the most interesting results. So if you want to know more details, you are welcome to go there or talk to me. So I'm going to... right. I'm just going to introduce again what Brondors are to keep everyone on the same page. Also a little of historical that I really like. So until like 30 years ago, we didn't know Brondors. We knew that they must exist, but we have never observed it actually. So we knew that, well, we knew, of course, the stars being the most less massive stars indoors with masses down to 80 Jupiter masses. And of course, we knew the planets of the solar system being the most massive planet, Jupiter. But in between, there was a mass gap between stars and planets that Brondors were expected to fill. In 1985, Brondors were simultaneously discovered with the first exoplanet. And since then, more and more Brondors have been discovered, filling like all the gap in mass that we had back in the day between stars and planets. Now we have several thousands of Brondors with masses between 80 and 13 Jupiter masses. 13 Jupiter masses, as we were talking yesterday, this is the canonical lower limit, but we can discuss it, of course. And we have three spectral types between all the Brondors, the L's, the T's, and the Y's, with a spanning temperature between 2600 Kelvin and 300 Kelvin, or even longer. If we plot Brondors in our favorite color magnitude diagram plot, we have L dwarfs in this part of the color magnitude diagram. Here we have T dwarfs, and of course, in between part, this interesting part of the color magnitude diagram, we find the L transition in which T dwarfs, in spite of being colder than L dwarfs, they are bluer. But what I want to really remark is that at the L transition, what really happens there is chemistry, as we were talking about before. And what actually happens is that the carbon monoxide converts into methane. So the main characteristic of the start of the L transition is that we find methane in the spectra of Brondors. So keep that in mind because it's going to be important for later. And of course, down here we have the TY transition that I'm absolutely not going to talk about. I hope you yesterday saw the Splinter because it was super interesting, just dedicated. So what is our H benchmark sample? We are talking how important benchmarks are. And I'm going to show three of these benchmarks. And these are benchmarks not only because two of them are gravitationally bound, but also because we know very well the ages of these objects. So these Brondors are actually not as mysterious as the other Brondors that we have out there. An important thing is that we know the age very well because these are members of the TW Hydra association, which is about 10 million years old. We have very little Brondors with this age, with this super young age. So that's also very interesting. The lucky sample is the following. So it's three objects, two Brondors, and one planet. The first one is TW 28, which is an M9 Brondorf, intermediate surface gravity, and a mass of 21 Jupiter masses. And it has a disk. This was found way before the JWST observations were done. Then we have TW 27A, which is also an M9 Brondorf, and same mass, 20 Jupiter masses, also with a disk, but a smaller disk than TRE 28. And finally, we have TRE 27b, or better known as 2MASS 1207b. This might sound familiar to most of you because it's the first exoplanet, directly image exoplanet, that was discovered back in 2005. And the spectral type is about L6. But actually, there was not such a good spectrum as this that I'm going to show until now. And the other interesting thing is that it was known because this system was observed with ALMA before, is that if TWA27b has a disk, the disk is going to be super low mass, and the upper limit estimated for that is 1 mass of the moon, so very low mass. So one of the GTO programs with the WST, we observed these 3 objects using the NearSpec IFU, which has a resolution of, well, with a configuration that has a resolution of 2700, so pretty high resolution, and we cover all the way from 0.97 to 5.3 micron. So without further ado, I'm going to show how John Randolph spectra look to the eyes of JWST. And I'm going to start with the blue part. I'm not going to go through all of them because I could be talking for 2 hours. So I'm just going to show the nicest parts. This is the bluest part. We have 28 on the top, 27A in blue, dark blue in the middle, and 27B at the bottom. I was not able to appreciate how cool these spectra are and what's the awesome quality of this spectra until I actually overlap what I'm supposed to see here. So these are probably most of the spectral features that we expect to find in this spectrum, and most of them correspond to some wiggles, which is amazing. So everything in the spectra is something. This is not noise. So of course, that's amazing for the 2 brown dwarfs, the 2 young brown dwarfs. But what really amazed me the most was the spectra of TRE 27b, because in principle it looks pretty noisy, but there are some characteristics that we saw that I've never seen before. And I'm going to highlight them for you. We find Paschen gamma, helium, and Paschen delta. These are emission lines. This is, I remind you, 5 Jupiter massive planets. These emission lines are telling us that 3720b has a disk. You know, we can consider this. And it not only has a disk, but it's also accreting. This is a planet, okay? I will highlight, this is a planet. And if I continue moving towards the red, we find Paschen beta, and we also find Paschen gamma. So this is blasting with lines. It's crazy. So if you want to know more, you can go to the paper or to the paper of Luhmann 2023, in which he does more thorough analysis of all these lines. What I really focused on this paper was on comparing to model spectra, because we know that models struggle to reproduce young brown dwarfs in general. And if we go all the way down to spectral types close to the LT transition, then hot party can be happening there. So I took 2 families of models, the BT-settled atmospheric models, that are cloudy models that have disequilibrium chemistry, and the ALMA atmospheric models, which are cloudless models. They also have disequilibrium chemistry with turbulent mixing and everything. So 2 different families of models, see how they reproduce our spectra. Spoiler alert, you can go check all the details, but the two M9 brown dwarfs are pretty well reproduced. Of course, the trouble starts when we want to reproduce the spectra of TRE 27b. So here we have in blue the spectra of our L6, of our planet, and the 2 models. As you have probably noticed already, there is the meshing feature here that both models predict that should be there. But we don't see it in the spectrum. If I move forward to the range between 4.4 and 5 microns, both models expect to have stronger CO assorptions, but actually the spectra doesn't show any. And you could be thinking, oh, well, the models are wrong, right? Because the observations are never wrong, we know it. So this is part of what Newman presented in his 2023 paper. He compared the spectra of Telluride-27b with two other spectra of two other objects that are similar spectral type, but much older, or relatively older. So the first one is PSO 318, which is an L7, and it's 23 million years old. And the other one is VHS 1256b, which is 115 million years old. So if we go to our preferred features here, we see that methane is present for PSO 318 and for VHS. And we see the CO band for VHS that is a lot deeper than for our object. So what is going on here? My theory is that Telluride-27b, because it's a lot younger than the others, even though it's the same spectral type or similar spectral type, has not reached the electric transition, meaning that probably at the very young ages, the electric transition starts at later spectral types due to the fact that the gravity is just lower. Of course, this is the only object that we have, so we have to populate our color magnitude diagram and do this for more objects to actually confirm this. But that would be one of the things that could be going on. So with this, I'm going to reach to my conclusions. So the near-spec spectra show all the atomic and molecular bands expecting for Jump-Run dwarfs, and some of them, as you saw, not expected. In particular, Telluride-27b shows emission features pointing to the existence of a protoplanetary disk. And the framework reproduced very well the two Rondorf spectra, but not the planet. And in particular, these atmospheric models overpredict methane and CO, probably due to the electric transition be delayed for very young dwarfs or planets. So if you want to check all the details, scan this QR code. You can also download your data from there, and you can have fun, fit your favorite models. And yeah, please ask me any questions. Thank you. Question. Yeah. What are your condition features? Right. I don't have that on top of my mind, but it's on the Luhmann 2023 paper. So yeah.
I have a question that will maybe so is it possible that what we are seeing here is because we have isothermal upper atmosphere that cause the accretion, so that all the CO absorption feature that disappear the isothermal. So in the isothermal profile, you won't see any of them. You need a temperature gradient to see a CO.
Would be.
Since this is the buddy system, Splinter, I'm curious for the 1207B. Did you check that there was no contamination from A? And that it wasn't like some weird orientation where we're just looking at the disk of A somehow, that's contaminating B?
They are too far from that. They are like decently separated.
It was really well separated.
Yeah, yeah.
Spectra,
yeah.
And you got the acquisition image, we're totally sure.
Yeah, so we use actually 20. Oh, yeah, 100%. 28 was used with, you might be wondering, what do you observe 28? 28 was observed because it was similar spectral type, similar characteristics to 27A. So we could basically subtract 27A with 28, sorry, and remain only with 27B. So that was the way with the observation.
Thank you, Megan. I think it's gonna.
Right. This is good. Okay. All right. Okay, thank you. All right, can you all hear me?